Hello students, this is Professor Chalai, and in this video we're going to start looking at the basics of quantum mechanics by talking about the de Broglie wavelength. As always, you can follow along with our chapter 6 workbook, and by the end of this video you should be able to describe the de Broglie wavelength and relate this wavelength to the particle's mass and velocity. Let's get started. And to get started, let's look at where we left off last time when we talked about the Bohr model. So we talked about how the Bohr model was necessary because we saw these line spectra in the emission spectrum of different elements, not a continuous spectrum. And the reason that for the line spectrum, according to de Broglie, was that the electrons orbit the atom around the nucleus in these fixed orbits, and they emit energy when they jump from one orbit to the other. So let me draw that somewhere again. Let's draw that right here. So, if we have the nucleus of the atom here, these electrons are only in these fixed orbit, and when they emit energy, they go from a high orbit to a lower energy orbit, and they emit energy. But this doesn't really make much sense, does it? Like, how does it move from this outer orbit to the inner orbit? Does it just disappear and then appear? If it can't go anywhere in between, where does it go? That doesn't seem to make a lot of sense at all. Things don't just disappear, right? So while it did explain the line spectrum very well, it's not a very satisfactory explanation of what the electron does. But we do have a way to describe the motion of electrons that does have this discrete change in energy that doesn't require the electron to just disappear and appear somewhere else. And to talk about how that description is the foundation of quantum mechanics. And basically what we do then is we describe the electron as, instead of a particle disappearing and appearing somewhere else, we'll describe it as a wave, right? So to understand what's going on, let's go back to this idea of a standing wave. So this is an example of a standing wave where it's a wave trapped in a box. It's trapped because the two edges are tied down. You can imagine this is like a string, right? Where the two edges are tied down, and so the string is just vibrating. This is a standing wave. So if I were to sort of think of this as a wave, right, then this is one wavelength, right? This is one wavelength. Then what we see there is just this part of the wave. So what we see is half of a wavelength. But we can make this standing wave have even more energy. Let's run this. It's going to take a while. So we know that the shorter the wavelength, the more energy it has. So the wave that we just saw was half a wavelength, which will have some amount of energy. Let's call it E1. Then we're still running. Then what we'll see is, for the next level up, we'll see a wavelength that is one full wavelength, not just half of a wavelength like we did before, but one full wavelength. So we'll have an energy of one wavelength, and we'll call that E2. There we go. There's my full wavelength energy, right? The edges are still tied down, so the edges can't move. So this is the kind of wave we can expect for this wave trapped in this box. So you can think of electrons as the same way, as a wave, the electron moving as a wave trapped in the box of the atom, if you think of it that way. And so the electron can have this amount of energy and this amount of energy, but it can't have any energy in between because, let's look at it. We could have half a wavelength because these two edges are tied down and then this part is left to oscillate. Or we could have one full wavelength because these two edges are tied down and then this oscillate back and forth. But there is no way that we can create a wave where, for example, something like an edge like that is tied down, because then this wouldn't really be a wave trapped in the box because this edge is not tied down. I hope this is all making sense, but that's how the idea of an electron moving or behaving like a wave can have these types of energies without having it disappear and appear somewhere else. They just have discrete energy is what we say. So that's the idea behind the foundation of quantum mechanics, that electrons will move as a wave. But you might be asking, well, if the electron, or anything really, according to quantum mechanics is a wave, what is the wavelength? Because all waves have a wavelength. Well, to answer that question, de Broglie sort of came up with the de Broglie wavelength. Now, obviously, in this class, we don't derive how we get all of these different wavelengths, but this is the equation for the de Broglie wavelength, right? Lambda here is the wavelength. So let me just write that. So this is the de Broglie wavelength. Because it's the length of the wave, usually we measure that in meters. So meters. H is Planck's constant, right, which is 6.626 by 10 to the minus 34 joules times seconds. Or you can write, remember 1 joule as 1 kilogram meter squared per second squared. So you can write this in terms of similarly as 6.626 by 10 to the minus 34 kilogram meter squared per second to the first power. And this will come in, these units will come in useful when we want to cancel out using mass. Okay, m here in this equation is the mass, right? And usually that will be in kilogram because we want kilogram to cancel out with this kilogram up here. And then v is the velocity. And velocity is in meters per second. So most times that we'll use the de Broglie wavelength, it is for the electron, because that's really the quantum mechanical object that we're most interested in this course. So the mass of the electron with m, symbol is m with a little e, is 9.1094 by 10 to the minus 31 kilograms. It's a very, very tiny mass. If you're looking at the de Broglie wavelength for anything, it will be the mass of that object. Okay, with that, try to calculate the de Broglie wavelength of an electron traveling with a speed of 2.56 by 10 to the 6 meters per second. You have the equation above. See if you can try to do that on your own. You can pause the video now, unpause when you think you have the answer, and we'll go over it together. Okay, so we talked about how the de Broglie wavelength is equal to h times the divided by the mass. In this case, it's an electron, so it'll be the mass of the electron times the velocity of the electron. H we know is 6.626 by 10 to the minus 34. We'll use the units of kilograms meter squared per second, right? Divided by the denominator, the mass of the electron is, we know it's from up here, 9.109 by 10 to the minus 31 kilograms, such that kilograms will cancel out there, multiplied by the velocity of this electrons, which is in meters per second here, 2.56 by 10 to the 6 meters per second. So per second cancel out with per second, meters cancel out with one of the meters, and so the wavelength is in the other meter that's left over. And you punch all of these into your calculator, and I get 2.84 by 10 to the minus 10 meters. That's the wavelength. That's a very, very small wavelength of this electron, but this is, you know, about the size of an atom. So wavelength of electrons might be small, but from the perspective of an atom, they're very important. That they actually, from the perspective of the atom, the electron does really move like a wave. Okay, try number 11 on your own. Here we're asked to calculate the velocity of an electron with a de Broglie wavelength approximately equal to the length of the chemical bond, which is about 1.2 by 10 to the minus 10 meters. See if you can figure that out on your own, and then you can unpause the video and we'll go over that together. Okay, so we know that the de Broglie wavelength equation is lambda is equal to h over the mass of electrons times the velocity. Here, they give us the wavelength, which is 1.2 by 10 to the minus 10 meters, right? Then we know h is Planck's constant, we always know that. We know the mass of the electron, so we're asked to find the velocity. So let's rewrite this equation to solve for the velocity by multiplying by the velocity on both sides, right? And then dividing by lambda on both sides. And so what that means is that the velocity is equal to h divided by the mass of the electron times the wavelength lambda. So let's plug these in. 6.626 by 10 to the minus 34 kilograms meters squared per second. The mass of electron is 9.1094 by 10 to the minus 31 kilograms. 2 kilograms cancel out. And then the wavelength is, we have here 1.2 by 10 to the minus 10 meters, such that meters cancel out with one of these meters. So our remaining unit here is meters per second, which makes sense. We're calculating velocity, which is meters per second. And so the answer in meters per second will be 6.1 by 10 to the 6 meters per second. So that shows how fast the velocity of that electron is. It's about 6 million meters per second. Okay, finally, this de Broglie wavelength could be applied to anything, not just electrons. Everything has a wavelength according to quantum mechanics, including you. So let's try to calculate your de Broglie wavelength. Let's assume that you have a mass of 140 pounds, right? And you're driving in a car going 80 miles per hour. So that's your mass and that's your velocity. What is your de Broglie wavelength? Spend some time trying to figure it out, and when you're done, we'll go over it together. Okay, so we know that the de Broglie wavelength is h over m times v, right? H is Planck's constant, m is your mass, v is your velocity, but your mass should be in kilograms, and your velocity should be in meters per second. Here they give us the mass in pounds and the velocity in miles per hour, so we need to convert those. So let's start with the mass. So the mass, which is 140 pounds, we need to convert to kilograms. We know that, what do we know? We know that 1 kilogram is 2.205 pounds, so that was easy. This will give us about 63 kilograms to 2 sig figs. All right, let's try to figure out the velocity. Here we have a velocity of a car going 80 miles per hour, and we need to calculate changes in the meters per second. So we might know that 1 mile is 1.609 kilometers, so that'll help. And we know that 1 kilometer is 1,000 meters. So that will give us the meters on top. Now we need to convert hours to seconds. We know that 1 hour is 60 minutes, and 1 minute is 60 seconds. So minutes cancel, hours cancel, so this will give us meters per second. And if we plug all of this into our calculator, I think we get 38 meters per second. Okay, so now we have the mass in kilograms, the velocity in meters per second. We can solve for the de Broglie wavelength. And it will be Planck's constant h, which is 6.626 by 10 to the minus 34 kilogram meter squared per second, divided by the mass. In this case, the mass is 63 kilograms, so kilograms cancel, and times the velocity. Velocity is 38 meters per second. So let's see what happens here. The per second cancels out with the per second. The meter cancels out with one of the meter, and so we're left with just the other meter as the answer, which makes sense because it's a wavelength in meters. And the answer that I get is 2.8 by 10 to the minus 37 meters. So that's your wavelength. It is such a ridiculously small wavelength that it would be not applicable to anything in everyday life at all, because it's so tiny, 10 to the minus 37. But that is your de Broglie wavelength if you're acting as a quantum particle, a wave. All right, so that'll brings us to the end of the de Broglie wavelength. In the next video, we're going to go deeper into other aspects of quantum mechanics when we talk about the uncertainty principle. We'll see you in the next video. Bye.